I think for the talk today, thanks very much for coming. Thank you. And thank Andy, thanks Matt for the nice organization. Today's talk, I will be switching between Blackboard and the slides, and depends on the audience understanding. If I didn't make something clear, and I will switch to the other one, vice versa. So please feel free to interact with me. So maybe let me begin with a little bit slides. So maybe I don't need to draw too many things. I just show you slides. Yeah, so the title, as you see, is a weak parity violation, which is the weak force does not respect parity symmetry, and it's actually maximally parity violating. In the sense, the weak force coupled to the so-called left-handed right biofermion in the standard model. And strong CP problem is a problem of the strong interaction, strong force. Potentially should have some possible CP or T violating term, so-called the theta term. But in no vacuum, we did not detect that. So it's a strong CP problem. And symmetric mass generation is a concept many people in the audience actually explore. It's a concept that when the system within certain global symmetry, let's say G, such that this symmetry G is anomaly free, then if you start with any phase, like gapless phase, free fermion or conformal field theory, CFT phase, there exists certain deformation going from, for example, symmetric gapless phase to symmetric gap phase, and possibly go through some transition called symmetric mass generation transition. And while the symmetric gap phase is something that evolving just a single ground state, which means unique ground state is number just one, and then maybe possible energy gap above the ground state and possible other excited states. So the point is that go from the gapless phase to a gap phase through a process of preserving the symmetry. Well, I'll go in this symmetric mass generation detail, but the important part is that interaction is evolved. In a sense, it's not a mean field quadratic mass term type of deformation, but highly interacting deformation. So I quickly explain this three concepts that we will encounter in the talk, but I will try to say they could have a very tightly relation between them, and I'll have a proposal to see this three problem or three things at one time. Okay. Right. So any questions so far? Yeah. So actually, works has been done since I was in grad school at MIT. You see the papers 2013, and till there's many more recent paper actually also already 2 or 3 years ago, but I don't think as many people know what I'm doing. So I feel like it probably is good to talk about this a little bit more. Okay. Right. Yes. BKT transition? Yeah. What's the question? BKT transition? I think BKT is more well defined in 1+1D, right? So we will consider more general. Huh? Not sure. I don't necessarily know it's always BKT. Yeah. I guess you are trying to say the property of correlation functions. I know some of the example, like 3450 model in 1+1D we'll discuss, will be BKT. Yeah. It will be BKT for that example, but I don't know in general. But it's a good question. Yeah. But the main point today, I think I would most explore this phase, go to this phase. Well, the transition is not a main concern, but I will comment a little. Okay. So actually, the thing we require is a full standard model. In a sense, maybe you took some classes here in Cambridge. I think David Tom probably gave a nice lecture. You might listen to some of them. So we will need all the standard model, the knowledge, and in a sense that those are things award the Nobel Prize, and we are putting in there. So anything has been awarded Nobel Prize, we will take it for the standard point. But anything haven't, then we will question, we'll challenge them. So one of person actually was very relevant for the weak parity violation is these two people, Li and Yang. And if you know the news, actually, Xi and Yang just passed away, unfortunately. In his 103 years old. Yes, and he has won Nobel Prize in 35 years old. And he almost lived 70 years after he won Nobel Prize. And yeah, TDD, I think, passed away in 93 or 7, I forget. But it's also very, and he won Nobel Prize in 30. So this parity violation is exactly what we are having for the title, the weak parity violation. So we'll go there. Let me just directly say that, is that if you write down the biofermions in the standard model, you will find out that there's a left-handed one or right-handed one. It's a convention actually, but we just say that there are some left-handed one, right-handed one, such that combined together they become d-rock. But the left-handed one has a particular purpose to say left-handed because the way it coupled to the gauge field is actually important. In the sense, the difference is that the important part is that when the biofermion coupled to SU2 weak and U1 hypercharge, you can check, I will show in the table that they have a chiral charge. In a sense, you cannot see the left-handed charge, left-handed biofermion charge and right-handed biofermion charge match. For example, here, I draw this just the red, green, blue, like 3-color in the up and down quark. So this is a cartoon here. I'm counting degree of freedom of biofermion. And for mathematician like Mingyong, he know the spin group, spin 3,1, the Lorentz group in 3 + 1D. There's a representation for the biofermion is a 2-component complex. So when I write this biofermion, I mean the 2-component complex spinner in the spin 3,1. But for physicists, we just say these are biofermions. And when there's a left and right, become d-rock. But main point is that even though the SU3 color, you see they are pretty symmetric for the left and right, but the doublet is not. So actually the SU2, the left-handed biofermion coupled to SU2, and such that they are SU2 doublet, so it's 2-component. But the right-handed one is SU2 singlet, which means X trivially. And same thing for the left-handed lepton, which is a pair of neutrino electrons, while the right-handed one does not couple to SU2 weak. Okay, so this is a fact that we will come back again, more detail about the disparities violating because actually weak interaction SU2 coupled to the left-handed biofermion. But in addition, we should also mention that U1 hypercharge also is a chiral. In the sense, the U1 hypercharge is also not symmetric respect to the left biofermion and right. Okay. For example, some particle physicists prefer to normalize hypercharge in this fractionalized way, but we can normalize in the integer. Yeah, sorry, I didn't make an integer. You can just multiply by 6 times, so it'll be integers. Anyway, so this number is not symmetric between the parity transformation, flipping left and right. So that's why the U1 hypercharge is violating. Okay, so this will be the main thing, actually will be important for the parity violation. Other part of things will be rather for writing down standard model, but you can worry later. So just for this slide. Okay, so let me just write down this in terms of representations of the SU3, SU2, U1 Yang-Mills theory for the standard model with the 15 vial, possibly plus, or maybe not, with the right-hand neutrino, which we have not found. And all these representations are drawn in terms of cartoon, and their quantum numbers are here. So the main point is that you can see SU3 is symmetric respect to parity, but in a sense, this is symmetric. But the U1 hypercharge is not. So this number is not. Sorry, between the D quark and the Q, and the Q is the doublet of U and D for the left-hand one, and also this U quark. And same for the others. This is not. Okay. All right. So now I would like to mention that we are pretty on the good ground that most of the things people predict about the standard model actually is verified, including the last found new particle T quark and Higgs found in 1995 and 2012. But there are some parts of which we will concern today is the strong CP problem, and people actually try to give a solution based on so-called axiom. And also, I want to ask about the P and CP violation, whether there are some new hints, possibly from perspective, which I will allude to the symmetric mass generation. Okay. So, any question? All right. Yeah. So I also just systematically write down in terms of table, so you can pretty much see that the SU2 is not symmetric between the left and right, and the U1 hypercharge as well. Yeah. Okay. So with the previous cartoon summary, I write down a Lagrangian for the action of the action. integral full manifold standard model. So this is the Yang-Mills terms. So everything we will include standard model means we have these terms, all these things in the Lagrangian. So Yang-Mills was the one for the U1, which is Maxwell, and 2, 3 are the SU2 and SU3 gauge group Yang-Mills, which is weak and strong force. And then the coupling, everything should be written as the most convenient ones, the Weyl fermion, which is a 2-component complex, and coupled to the gauge field appropriately based on the previous slide representation. So you know how to write it down just based on that representation. And also there's a Yukawa-Higgs coupling between the left and right fermion. In the sense, in the standard model, the mass of the Weyl fermion is obtained by pairing the left and right to Dirac fermion and get a mass when the Higgs has a VAF. And there's a Yukawa-Higgs term. Other than that, there's a Higgs potential, and Higgs also coupled to the SU2 weak and U1 hypercharge. Okay. And the strong CP problem is questioned whether this zeta term is there, and if they are not there, if we have not measured that, and why this zeta are small. And the measurement is based on so-called neutron electric dipole moment, which is the experimental perspective. We will not touch today. We'll just work on theoretical side, thinking about whether this zeta term is there in the standard model. If not, can we give an interpretation? Okay, please. That's right, yeah. So 1, 2, 3 is for U1, SU2, SU3, and F3 is a field straight for the SU3. Okay, so far it's kind of boring, so Mignon is kind of a feel not so interesting, but let me get to something now. Yeah, I think let me just summarize where we are going. So actually I mentioned that. So weak parity violations, a weak force coupled to the left-hand Weyl fermion, and strong CP is why the zeta of that, the one we just write down, is small or almost 0. And now I'll try to relate these two puzzles in the weak and strong sectors as the possible mechanism for symmetric mass generation. In the sense that it's a matter field like fermion acquire mass without spontaneous symmetry breaking, but actually get a mass through some interaction. That interaction is beyond quadratic mean field or Yukawa-Higgs type of term. And this will work within the anomaly-free symmetry sectors. And now actually work on dimensions, not just 4. Maybe I will mention more about 2 dimensions because the audience like Lauren and Frank might be more interested in 1 + 1D, and I have a concrete model related to this 1 + 1D 3450 model. Okay, so that's where we are going. Okay. So so these are some of the reference for the parity violation. Basically, it has done for many years in the past. Yes, please. Ask anything.
Massless ones becoming massive walls.
Yeah.
At low energy.
That's right. Not really. That's not the way I would say that. This is for the confinement. So this is dynamic for the gauge field, right? Symmetric mass generation is a fact that for matter field, even just for fermions boson, like spin 1/2 fermion or spin 0 boson, it's not through the dynamics of the Ronin coupling like Yang-Mills. Yeah, so it's different. So I'll give an example for a set of fermions, just like the fermion in the standard model. The way we get mass, we only know through Yukawa-Higgs, and Higgs has a VAF, right? But I will give a different way to have a fermion have a mass through interaction. And even if you turn over the gauge field, you can still have the symmetric mass generation within fermions or within some other matter field. Okay, so these are some reference. Yeah, let me think, how do I proceed? So maybe for the moment, let me swap to the kind of let's see. Let me swap to Blackboard a little bit. So maybe. Yeah. So let's I have a summarized standard model. So let's just go to the kind of punchline where we are going in the end. And if you stay long, then we'll be there. So I want to propose a model goes like this. Sorry, where's the? Anyway, I think. is there? Yeah, I want to propose a model more or less like this. So we have our world of standard model. Everything we have measured so far is a 3 plus 1D standard model, living in some of the 4-dimensional manifold. Locally, maybe just as we know, like Riemannian manifold, very flat. But globally, we don't know. Right? As long, just the point is like there is some large size of 4D, and I want to consider the other side, like strip, which like condensed matter is like a cylinder, and whether there is some compact boundaries, not so important, but if you consider finite universe, sometimes it's easier to think about something like the strip, such that this width is finite dimensional, 5th dimension, but it's finite. And in a sense, it's finite, so it can actually shrink to arbitrarily small for the purpose. And such that on the other side, there is something called the mirror universe or the mirror standard model. So to make it more clear is that actually has a lot of connection to condensed matter physicists when they study quantum Hall states, which I'll make an analogy very soon. So let me actually just draw it anyway. So 3 plus 1D standard model, 3 plus 1D mirror standard model. Okay, so let's make an analogy for condensed matter. It's also a strip, but now it's easier to understand. So this will be 1 plus 1D. And this might be some chiral fermion theory. And then there's a mirror, yeah, 1 plus 1. In my drawing, yes. But I don't think for my argument it's important. I draw it just make it finite, yes. Yeah, I think if you are like mathematician, you need to think very complex geometry topologies. But this is just easier for people who want to simulate, for example, on the finite size system, then we put on cylinder stripped. So this will be 1 plus 1D chiral fermion. And there's a so-called mirror fermion, which is also chiral, but the chirality is opposite. So if I draw the chirality, let's say this is a left-handed one. If I define the dimension of this as x, actually maybe because this left hand this way, then I define x probably this way. And then there's y. There's something like this. In this case, I have a plus x, y, z here. And then there's w. Maybe I put w here. So width. So because standard model is higher dimension, so maybe people think it's too complicated. So let's go here. So we can actually put a U1 level 1 Chern-Simons theory as integer quantum Hall state. And it has a charge 1, central charge Cl equal to 1 biofermion going this direction. But because there's a mirror stripped, the central charge of that is equal to 1, but it's right-handed 1. And the C dot plus C right is the total central charge, and C dot minus C right is the total chiral central charge for the whole system. So if you have C dot minus C right for the whole system, it's certainly 0. Okay. So far it's easy. But now let's go next step. For people who study topological insulator superconductor know that this kind of things that you write is actually something called Chern insulator with appropriate couple in hopping between regularization and some lattice, then can UV complete that. And there are some fluxes for the phases of a hopping term that required to make the chiral fermions running on the edge. And for the chiral fermion, I think many talks in the conference already people explore that it's just psi L partial T minus partial psi L for the left-hand one. And for the mirror one, then we do psi R bigger partial T plus partial X psi R. And I use prime to indicate the prime is the mirror. Okay. So this will be a series, but remember they are slightly off some dimension. So if this is along some direction, then this will be something at some location at let's say W equal to W. Let's say just W prime or something. Yeah, just some kind of keep this 0 and this W prime. Okay, so this is the situation. Okay, yeah.
Who chooses the width?
Who choose?
Who chooses the width?
I can choose. Yeah, I can choose.
Check time is too low.
That's right. That's right. Very good, very good. Yeah, very good. Thanks for the question. So you can just coincide and then it will disappear. Yeah. But this is a good question. I'm just going there. Hope I have enough color of choke. So actually, for people who study topological insulator superconductor, this is exactly a domain move fermion. So maybe I should not mix this with, this is a real space, X and W, and then with time direction, I didn't draw, it's 1 plus 1D. And on the boundary of 2 plus 1D, and there's a time direction, so it's X and W and the T. Okay, so he asked, what's your name? Start. Yeah, so start, anyway, start, okay. So he asked a question about how do I change the width, can I shrink it, okay? So you can understand this in terms of a mass profile along the W direction, and such that this is the mass. And what you need to do is that you have this fermions in 2 plus 1D. And if I remember correctly, it's a Dirac fermion. Yeah. So 2 plus 1 Dirac fermion, you can change the sign of the mass, positive to negative. And at this so-called domain wall between two of the gap vacuum but opposite, there's a 0 energy modes, or some people just call 0 modes. And in fact, this will be 1 plus 1D. And this has chirality. And if you try to integrate this Dirac fermion with positive mass versus negative mass, then Mignon will tell you this is exactly the derivation for using the Dirac operator integrate all this ratio to define the Chen-Simon term, U1 level 1 Chen-Simon. So that's exactly what happens. So topological phase like a U1 level 1 Chen-Simon, in this sense, it's just the 2 plus 1D Dirac fermion with this mass. And for the purpose of condensed matter, you may not think that way, but basically they're just UV completion of this, which can be put on lattice. Okay, so far so good. And so I was also thinking a little bit is that in 2 plus 1D you also have a Marana fermion. So can someone tell me if I Dirac fermion here, the Carl-central charge here is central charge 1. If I change this mass to the 2 plus 1D Marana mass, can I tell you? Can you tell me what's the Carol fermion here? What's the central charge? Carol central charge. You must know. Yeah, you must know. So quickly, if it's Marana mass instead of Dirac mass, what's the Carol central charge here? There's a Carol fermion. There's a Carol fermion with opposite Carol central charge. So this will not be vial, but will be half of vial. Tell me, what's that fermion? Frank. So Marana is real. So this is 2D is this is 2D is 2-component complex, and this one be 2-component real. And when you reduce to 1 plus 1D on this domain, well, this will be vial fermion as 1-component complex. So degree of freedom is half of a 2C. So how about if I use the Marana as a mass? What's this? Quick, half. It has half. So it's 1-component real. And how do you call this fermion? How do you call this fermion? Half of vial fermion, real. That's right, Marana vial. That's chiral. So what's the Carl central charge? Half of that, 1/2. Anyway, so just 1/2. And yeah, so this will be just half of U1 level 1 in some sense. And you can write down, so it's not, it does not have a U1, in a sense, it does not have a U1 charge symmetry like vial fermion, but it'll be half of that. And it's actually gravitational Chen-Simon term you can write down. It's a real fermion. It does not couple to U1. It does not have a complex phase. Okay, so that's it. So we kind of just need one analogy here as the most basic slides we need. But we will start to stake them. So we'll stake one more time such that we may change the U1 level 1 to U1 level -1. And then with another layers of fermions. So I'll do again by just drawing another layer. And yeah, if I draw another layer, and if I swap the orientation, then actually I can have left moving here, I can have a possibly right moving, right? So let me do this way. I'll just claim that I'll put the four layers and with such that it's U1 level 1, U1 level 1, and U1 level minus 1, U1 level minus 1 consignment. But for people who know this picture, then you just take 4 times of this. And the domain fermion need to be this way and this way. But people who are smart know just can see the addition of the vacuum or eta together exactly cancel. Originally, they are topological phase, which is invertible TFT, invertible topological field theory, or topological insulator in this case, protected by U1 symmetry. In some sense, this is not quite topological insulator. It's really integer quantum hole. So which means it has certain long-range entanglement, but roughly speaking, still there's a different definition one can have. But anyway, the main point is like this layers of a invertible field series, when I stay 4 times with positive and negative like this 4 times, actually can cancel out. And you will say, why do I do this? Kind of boring. But I can assign the U1 charge slightly differently, such that it's not this U1 level 1, but the U1 symmetry charge for vial fermion. And that's the famous 3450. I can take charge 3, 4, and 50 for the fermion, such that this is 3 for the lab moving, 4 for the lab moving. So important part is that it turns out that this vial fermion with 4 vial fermion, 2 left and 2 right, U1 symmetry such as this, it has interesting property in high energy physicists who knows anomaly cancellations, total anomaly of global symmetry. They will know this diagram for the U1, 0. In a sense, the gravity also 0. And that's actually turned out to be the only anomaly in this 1+1D theory. Because nowadays people know how to classify anomaly based on so-called Bodism group or co-Bodism. And that writing turned out will have something to do with a topological phase of Bodism group defined with a spin structure at times U1 mod Z2 or spin C structure in 3 dimensions. And for people who know Bodism group, then it's actually a combination of omega 3 for the so-called free torsion part, which is number 31, plus omega 4 for the spin. And it turns out only have a Z class. But for people who don't know, it's fine. Just that there is a 2Z class that's captured by these 2 diagrams. And the anomaly is canceled because this one is due to the Pythagoras law. Because the anomaly calculation for this will be exactly the whole conductance Frank would like to compute for the quantum Hall states. Because this one computation will be Q and whole conductance for the K matrix for the U1 consignment K inverse Q over 2 pi. If I turn 2 pi here, then this is exactly its diagram. And that means anomaly free means the whole conductance cannot transpose. It means the Leflin's thought experiment, when you insert the U1 flux, then there's actually no charge transpose. Even though maybe fermion can transpose, but charge is not transporting. So that's a surprising fact. If you go back to the usual Leflin flux insertion argument, which you swear the flux, actually that moving fermion can go to right moving and pump in 1. And that's the anomalous current, partial mu j, mu L minus J mu R is actually proportional to non-zero, proportional to the flux F, which is a 0, 1 component will be electric field. But in 1 high dimension, it's actually corresponding to the Faraday induction, the d phi dt over dt. So I'm just trying to relate something you know in condensed matter to the anomaly diagram for this group. So that coefficient is exactly the full conductance of anomaly coefficient. And I'm just saying that for this theory, it turns out 3450 is 0. So it means maybe fermion can secretly transpose, but the charge is not measured because the whole conductance is 0 for this theory. So that means it's anomaly free. Yeah, please. Oh, yes. Yeah. That's right. Because there is a fermion, which is spin structure, and there's a U1 charge, it's a U1 symmetry. And because spin and U1 share fermion parity, so that's why they model Z2F. Yeah. Yes. That's right. No. This Bodism group will classify the manifold with this structure, and that manifold can be used to detect the invertible field theory in one high dimension. But invertible field theory has one-to-one correspondence to the anomalous boundary class. So this Boltzmann group classify a manifold of that structure due to the Boltzmann relation, but also use that manifold to detect the invertible field theory. But the invertible, and then you class anomaly because yes, that's good. So then I say there's a Z2Z class, and it corresponds to these two diagrams. But for mathematician, will know these two classes generated by C1 squaring for this term, and the other term is Pondrian class P1, and the coefficient will be maybe over 3, depends. Or fermion, I think, may divide by 16. Yeah. So this is a 2 class generated by 2Z class. So I try to say this is a complete classification anomaly. So they will satisfy so-called symmetric match generation condition that I need to check all the anomalies is true to cancel. The major progress in the field of symmetric match generation is due to we now are confident about how to check anomaly completely. So once I know that, then I know how to check whether the theory has anomaly. If it does not, then if I go from symmetric gapless space, Riemanns have a way to go. Sorry, if I start from symmetric gapless space, then I have a way to go from this to the gap place. Yeah, and the reason is due to that this two phase should not be distinguished. In the sense, in a larger set of the so-called deformation class of the theory, that the phase diagram must have a way to connect symmetric gapless phase to symmetric gap phase through some deformation. And this deformation process will hint in the end of the phase diagram, phase boundary, so that two phases be identified. And that's due to the two theory share the same anomaly, and they don't have a way to distinct. Basically, the bulk, anyway, basically they are connected. Yeah. So the symmetric match generation is exactly the concept to check the system. If it's anomaly free, then they must have a way to deform a symmetric gapless space to symmetric gap phase. It's a way to do by principle. So what I'm drawing is more like a phase diagram of the quantum phases. And what now we are going to say is that the 3450 model, 3450 model in this side will be connected to a symmetric gap phase because we just mentioned that we check all the anomalies 0. And now the question is that can we gap them symmetrically and preserving the U1 symmetry, or just I'm going to say more, write it down. Yeah. So maybe I can write it down. Any question? Yeah, please. Yeah, please. Sorry. That's right. Correct. And if they are anomaly free and they have a same symmetry, there's a principle that they will be connected in the phase diagram. There's a way you can deform it. Even though in between, possibly this seems a gapless phase on this side, maybe it looks like there's some fake boundary between them, but in the end, there's a path. In the larger side, you can connect them. And this is a concept called the deformation class of quantum field theory. I think more famously, Nati Seiber gave a talk in Spring 2019, and he quoted this name. But I think in the field, many people are using principle in many places, and I work with this concept in many years, like in 2013 or 2018 paper, using this concept to deform this symmetric gapless to symmetric gap phase. Okay, so let's give a example soon. But yeah. Please. That's right.
There's a conjecture that
yes.
if two phases have the same anomaly, the same symmetry.
That's right. That's right. That's exactly this statement. So this defined deformation class, yes. So this is a co-deformation class. And if the most famous people who speak about this is Nati Seiber, I think, in 2019 Spring. But as I say, I think me and Wen, we start to use this principle to do this model since 2013. I think we try to prove something about the spin 10 granular theory, which is people call SO10 model. With spin 10 gauge group and also SU5 model, they have an anomaly basically by trading Boltzmann group with the fermion content. I mentioned that the Boltzmann group can be non-trivial, but you need to check the index for the theory. Which index, which you map to. If you map to 0, then you are confident it's anomaly free. Then what I'm going to say next, which I should complete a sentence. There's a mirror fermion on the other side, and there's a chiral fermion. They can start with all gapless. But this belief that you can deform this two gap phase can be applied now to any side on any side of domain wall. Certainly I can apply to two sides and it become all gapped. And it shouldn't surprise you, can read out the two vacua that become all flat, which just flat 0. But if I only apply interaction on or some deformation on this side, and I keep the gaplessness here, you can imagine what happens more picturesquely. You just move these two vacua more closer and then allow them to interact. But you need to allow interaction such that it's not pair one of the fermion, only is any of the other. But you may need to pair 4 of them, or even multi-body, 6-body interaction within 4 fermion on this side. Yeah. But how do you have a confidence this can work? You know, people have checked that and failed many times in the sense they don't know how to write symmetric gap, symmetric interaction. Even if they write something, they don't even know what is this gap. But we have this belief, this must be true. So if we didn't find it, we must fight harder, try harder. And the paper in 2013, pretty much my first paper at school is basically just try to work on this. Actually, was what Xiaogang Wen told me to think about this model, and it takes me 1 week. We just already write out the paper. It wasn't hard from condensed matter point of view, but I think there's some condition the Holden derived, which I will mention. I think Lohan will know. So I will write down this interaction term to get the 3450. Okay, but now I use this as a toy model, but the goal is actually 3000 is a model. So yes. Oh, yeah, okay, I'll go to stand models now. Huh?
I thought that this was applicable only for gap phase or traditional.
No, anything. Yeah, I think yeah, gapless as well.
But then you need to define stable gapless phases. Which
Yeah.
It's not so clear how they define that. Usually just
Yeah.
when the gap.
Right. So here I didn't draw the precise phase diagram, but for gap phase, I guess there is some fixed point. Maybe just one, and can just trivial gap. But for gapless phase, we don't know the region, so it can maybe have a, you know, something stable and flow to that, and maybe there are other things, and that could be a region. So I certainly just hand waving and say there is some phase for gapless. But I also try to say gapless. I want to emphasize it's not just people usually start with this gapless phase is a free fermion, and which is easy to write down, and also it's easier to count the indices. But for the CFT, you can also do that. So if you have a complicated CFT with complicated symmetry like monster group or something, if you check the anomaly for that is trivial in the Boltzmann sense, Boltzmann group sense, and you check the index 0, even though the classification of that is non-trivial, but if the index is 0, then you must know there is some deformation possible, even though it may be very difficult to come up with. But there's a topological principle we can prove, I'm going to say. I want to allude a little bit more about this picture. Actually, this is very, to me, I wrote a paper also about the lepton genesis. It's more like our universe thinking this way. If living on one side, like our chiral side, we can also have fermion flow on the other side by this frustrating argument. So in some sense, this picture helped me to think about the lepton genesis. And there is so-called different type of lepton genesis, like Dirac or Marana lepton genesis, but there's also gravitational lepton genesis due to the anomaly diagram, which I can just draw here. For standard model, I'm jumping a little bit, but standard model in 3+1, the U1 chiral fermion has 2 anomalies here. So one is U1Q, the other is U1 gravity square. So this concept of pulling things actually help to think about something is pulling the fermion from one side to the other side. If there's a mirror side, actually fermion can pump into the other side. I just make that comment, but it will coincide with like anomaly calculation, 3+1, the Weil fermion. For mathematician, this comes from a 6D polynomial, the C1 cube term, and this one will be C1 P1. And C1 is a chain class, P1 is a polynomial class. So we could just add trace R wedge R term, and this is F F F F F Q term. Okay, so the analogy for this is like the dimension differ by 2. Anomaly structure is not quite the same, but has some similarity. But now we can do something similar, which we will do. The kind of thing we will question in the end is that maybe the 15 or 15 plus 1, 16 biofermion in the standard model can also come from this staking picture of some stripped. And the geometry, again, is not so important, but more important is that there are vacua going from this side to the other side, just more like what I drew earlier. So use the yellow. And now I will do this 16 times. And actually it turned out, because the anomaly structure here is this way, which there's no pure gravitational anomaly like in 1 plus 1D. So actually there's no strict chirality in 3 plus 1D without U1 symmetry. So actually a 3 plus 1D biofermion, the left-hand one can change to the right-hand one. So what really defines the chirality in 3 plus 1D require additional internal symmetry, such as U1 or SU2 weak. And then that makes the theory really become chiral, because the chiral symmetry. And now I'll allude to a model. I'll go to the model. Invite you to think about this model with 16 layers of biofermion as a boundary of some strip. And for people now familiar with topological phase, they know the bulk will be a 5D bulk term. And this 5D bulk term has also a domain wall, and this will come to 3 plus 1D biofermion. And actually the bulk, you want to guess what kind of bulk fermion it is. So you have a positive mass here and negative mass here. And there's a zero mode, just the closing at this slides. So what kind of bulk? So these are massive 5D fermion. Anyone want to make a guess? 5D bulk fermion. So it will be Dirac. So if you have a 5D bulk Dirac fermion, then this will be 3 plus 1D bio. And it has certain chirality in the sense that with a U1 symmetry, then basically this will be a left-handed one, then this will be a right-handed one. And if I take a 15 plus 1 copy of that, it's standard model on this side, then I have a 16, the other mirror one was right-handed one. They couple to the standard model group in the chiral opposite way. Then the question, if they are also at low energy, then we should be able to see the mirror image of ourselves. Maybe we are able to detect them. But if we have not detected them, maybe there's a way to hide away. So this is where this concept of a symmetric mass generation come in. So now we want to deform this gapless phase to gap phase. But we should claim that actually there exists a way to replace this symmetric gapless phase to directly replace by the symmetric gap phase on this side. So then this side can be all gapped. Once the interaction is applied, so this can be gapped. Yeah. Same thing like there. So this can be applied to be gapped. So then we can actually obtain a mechanism to get a parity validation such that the chiral fermions only live on low energy. The whole system, not just on one side of the system, but the whole system. You can detect the whole system, the gapless spectrum only occur on one side of the edge. So this is how the parity validation may have explained, may be explained by mechanism that symmetric mass generation SMG on some mirror side. So this is like one part of the talk. But now we can show more detail, but this is the principle. So any question?
Two phases are connected by arch flow.
In some sense, yes, arch flow. In a sense, deformation by adding some interaction term. So you must modify the theory, not just the 1/8, but adding some interaction. So I'm going to write it down those interactions. And then when the coupling is small or perturbative, then actually you couldn't see that gapping can be done, which means they may still maintain to be gapless. However, when the interaction strays, the energy scale of the interaction is order 1 compatible with kinetic interaction, then it becomes non-perturbative, then you can deform to gap phase. Yes. No, just apply on the one part, the mirror edge. No, the boat is already gapped. So you see this picture. So this is a mass mass means like an energy gap. So these are O gap here, positive and negative gap, but gap is just 0 here. And I'm applying interaction between these gapless modes. Gap. So same thing for the standard model. These are gapless, nearly gapless standard model and nearly gapless standard model. If you think about before the electrical weak symmetry breaking scale, say above 250 GeV, when the Higgs does not have a bath, then this all looks fermion is really nearly gapless. But I want to say there could be some interaction at a scale much higher than 250 GeV before the Yukawa Higgs condense, before the electrical weak symmetry breaking. SMG is already there. So in that sense, SMG is more early universe than the Higgs condensation. And then in that case, parity violation can be explained. And it can come naturally, and anomaly structure come in, deformation class come in, and non-perturbative deformation also come in. So many things come in together. And this idea already connect the weak parity violation with SMG. But I haven't go to strong CP, but then it will come in again. Yes. 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 That's correct. That's perfect. You sound like a perfect understanding physicist. Yes. You're good. Yes, that's exactly. So that's a constraint of deformation required. We don't want to have a symmetry breaking. And it may have a multi-transition, possibly go somewhere. And the way to think about this for condensed matter people is that I need to add some high energy interaction, which means lattice scale interaction. And for physicists, it's like short distance interaction or high energy sector bring down. So yeah, anyway, so for some cases, people ask RG flow, then it's possible that the gapless phase is on this side. Then you might need to go up high energy somewhere, and there could be a model series somewhere. And it's harder to go gapless to symmetric gap directly. But if you have an excess more high energy mode, then you can think about this gapless sector might interact with additional high energy sector. So the interaction between this maybe also need to interact with this, not just within this interaction within this. And maybe this deformation might be done. Sometimes this can happen. Symmetric gap. But for 3450 model, it's not necessary. So that I'm going to, there are different perspectives, but it does not need to. Yes. Yes, that's also a good question. Yeah, maybe more connected to the possible phase boundaries. So this is another interesting direction. Yeah, we can talk about this. But today, Peter, I'm not exploring that. It's a good question. Yeah. Okay. Yes.
I thought it was important that the whole family remains gap.
Whole family.
You don't have any closing of gaps. Is that not true?
This will be true for classify the bulk gap phase. That's the invertible TFT or TQFT tabulation. That's correct. For this case, it's about deformation for also include gapless. Yeah. Yeah. That's what you say is about classification of gap phase. That's key. Yeah. Also classification of TQFT. But for me, actually, I'm deforming the theory. Yeah. 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 I don't know what that. Yeah. Yeah. Yeah, if I want to be more clear, maybe we can think about this more. Is that I'm putting here like 1 + 1D and 2 + 1D both. So if I call this is n dimension in D, then I can put this on the boundary for n + 1D bulk. And this, in principle, should be some invertible TFT. But now this is actually, I claim, anomaly is free, so this is a trivial class. And that means this is just the trivial vacuum of nothing. And I can remove this. And now I claim that between this one and any other side, if this is a trivial vacuum on the other side. So actually, I'm mixing the diagram. This is R3 diagram, but right now, let me erase that. Just thinking about the face. If I'm right now thinking about this n dimension D living on boundary of some invertible field. because this is trivial vacuum. So the other side is also a trivial vacuum. So then the two sides must be connected. And I try to connect in a way just by removing the boundary. Originally, there could be a gapless boundary here. Then this is just nothing. And this is just this gap also in ND. So that's a symmetric gap boundary. I don't know, does it make sense? Yeah. So yeah, there could be some subtlety or tricky to think more detail, but just I mean, I'm trying to relate them more intuitively. Yeah. Okay, so let me go to the. Okay. Really? Okay. Yes. No. Just graviton is, but they are just background field coupled to the matter field. Yeah. I'll make it more clear. Yeah. So no graviton is background. Gravity just the background gravity. Yes, it's on. Yeah, so quickly go to that. So we have shown one layer, right? There's a bulk we just draw here, but we put two layers. Then there's a way to add mass term between it's so-called Dirac fermion. And depends on the U1 charge assignment, you might get the usual psi L, Dega psi R term or the superconducting Parrington. There are different ways to write, but in some sense, these are not SMG. So this is familiar. But now, sorry, let me just go. Yeah, so then if I have 4 layers, wait. Sorry. Yeah, if I have 4 layers with charge 3450, then now I'm going to write down interaction. Give some argument about this. So on the gray side, basically, like a stick. Oh yeah, good. Yeah, I think so. So if this gray side is the interaction, then we just apply interaction here, and let's write it down. So interaction will look like applying on the mirror side like this. So there's AH on the chiral and BH on the mirror, and then these are the interaction term. So it depends on the basis you choose. If you just use 3450 as basis, there's one way to cook up just reverting 3450 in some way. In some sense, X by K matrix. You can show this will be U1 symmetric. In fact, actually preserve 2 chiral U1 symmetry. But the other, it requires to add 2 interaction term to break the remain 2 other U1 symmetry, because 4 biofermion have a 4 U1. You need to require to break 2 U1. So this interaction term has certain principle, certain rule that you obey, so that people have confidence to show this is the way to apply symmetry map generation. If you only think about RG, you don't have to believe that this interaction can gap it, but it's really gap it. So the reason for that, which I have another slide, I'll post on my website. The reason is that, but I draw another way, so I want to apply to the mirror. So this is a different slide. The reason is that there are a set of rules that make you check that this is the gapping term, and I can just say by principle. So more or less is the following: is that when I have the, let me also draw in here. When I have the chiral edge and the mirror edge here, you can think about this fermion field interaction term generated by something like bosonized term as cosine term. So the multi-fermion term like psi with possibly higher derivative can be bosonized, and it will become Seigerton term, cosine term, such that fermion will be mapped to the compact boson with this phase phi, and there could be some number in front. But then this cosine term may have a vacuum expectation value like the one I showed above. But this vacuum expectation of this can be achieved if this cosine term, in some sense, is compatible And what do I mean by that? Is that thinking about the U1, the U1 level 1 Chern-Simons theory, in some sense, this exponentiate of this phi boson term is essentially the endpoint of some line operator. If I imagine there's a bulk, which is the bulk I draw here, then you want to make sure that this line's end can have a VAF. It turns out that the condition to have the VAF to achieve is exactly the compatibility condition of the lines that you can end on the boundary, such that those lines that can end have a mutual statistic 0. And in some sense, for more mathematician kind of thinking is that you compute a partition function with arbitrary lines that can end on the boundary. So let me draw it. So these lines, if I use maybe a red color here, like these lines or the blue lines, you kind of imagine that this lines is ending on the mirror side. And then this goes like this. But you want to deform it, and possibly they will consider there are some calculations like this red line and blue lines are linked in some way. And then there's, and also it could have the intermediate linking in between. But if I define theory, for example, on this side, so gap phase, gap phase, then the partition function must be uniquely computable. And one way to assure this is true is this fluctuation due to the gradient statistics of this line operator is trivial. And this will be true actually, and it's exactly the condition imposed to write down interaction term. And this condition somehow for some reason is derived by Hoden, I think, 1995, long ago. And this condition is later used in many papers. They have a different argument, but in any case, so this will be the condition used. And there's also argument by like zero modes or gapping term of stability of the zero mode term, winding term. In my paper in the past, I derived that. So to show this is a condition. So that condition, once write it down compatibly, just try to find out some interaction term satisfy this kind of condition. Yeah. L is the coefficient inside the exponential of this bifield term. And K is the K matrix, which is the level of Chern-Simons. And yeah, so let me skip that. But the main point is actually these two conditions is pretty much related. And I think there's a deep truth about this, is that anomaly-free condition, which is whole conductance 0, and which Frank was studying with Laurent about this 3450, other than this U1, you can write another U1 made by K matrix or some sigma X matrices to the other U1. And these are also chiral. And then you can map Q1 and Q2 by K matrix, which is level 1, 1, 1, minus 1, minus 1 for this level. Because I was saying U1 level 1, 1, minus 1, minus 1. Then you map to this. And you can check all these four sets are independent. And the important outcome is another condition is this two set of U1 has self and mutual nullity free. So there are three conditions between this Q1 and Q2. You can check Q1, KQ1, Q1, K22, Q2, K22, all 0. And you can check the gapping term, which one can design, will be finding two set of L, satisfy the braiding statistic of two lines 0, and they will correspond to two independent interaction terms. So L1K inverse L1 and L1K inverse L2 and L2K inverse L2. So three conditions 0. But it turns out this L can be explicitly constructed from the U1s, the third and fourth U1, and there's a map between them. In some sense, construct these two will be explicitly breaking these two U1s of the additional U1. And it must be maximally you can preserve two U1, but you must break the remain. But minimally, you must have two interaction terms. So there is some the compatibility condition between maximum and minimum, and it's achieved exactly in this two set of two U1 separate in a certain way. So for string theory people, it's more like you are writing down Naron lattice of a chiral boson theory, and these are four-dimensional Naron lattice, and they are two subdimension, and there are some dual two-dimension, and such this two-dimension, they have exactly two different conditions to satisfy, but they can map to each other. So this two-dimensional space and two-dimensional space map to each other, and the two conditions are exactly mapped to each other. So a anomaly-free condition guarantee the gapping conditions. So this is a subtle part. And yeah. Yeah. I can make a comment, I think, just that for people who study this fermion rotor and fermion scattering, I think one can check even though the U13 and U14 is broken, there's a discrete Z5 and Z10 subgroup, Z5 times Z2 subgroup preserved, and that Z5 may have something to do with the fermion rotor scattering problem, this deformation line that David Tong talked about. In any case, if you're not there, if you don't know the code, it's fine. But then applied to the model we describe is that we think about our sector, which we are light, like low energy, so it's like a light sector. We live in a nearly massive sector, chiral, with this monomer-free condition. And then we want to hide the mirror sector, which we want to apply interaction here. And this two condition is applied to a dark sector. And the number of fermion here and here exactly match. And the preserved symmetry is actually cut the full larger symmetry to the space of half in some way, exactly half. And in the case of 3450, this will span the two subdimensional Naron lattice, and this will span the other two. And there's some interesting map between the two conditions. Okay, any question? Yeah, so this side is actually derived from Chen-Simon theory in the book. This side is from the anomaly-free condition, which is a whole conductance zero condition. Okay, so so now apply this idea. I guess I hope you get some confidence. Say when I write down some interaction term, actually I can reduce to something simpler. Earlier I was writing more complicated, but this is a simpler version of that. And yeah, so let me think what I'm saying. So I hope you have some confidence in this interaction term when the interaction stress or the energy scale is larger than it can get. But you may still wonder whether this is true. So I can give you a bit more like a scalar field Yukawa-Hicks-like perspective by introducing some dynamical phi1, phi2 field and couple to the fermion, such that phi1, phi2 are both dynamical field, and they should be fully integrated out. So this is more like a Fermi theory of 1 plus 1D, such integral this scalar field phi, it will give rise to this 6-body interaction. And you can show this 6-body interaction is exactly the multi-fermion interaction in the appropriate basis I write down earlier for the gap in the 3450 model. Because this is more like a quadratic term, so you can imagine that when the phi has a VAF, I certainly can gap it, and you don't have a worry. And now the claim is that when phi is disordered, which means phi does not have a VAF. So let me write it down. So when phi1, phi2 has a VAF, then you know it must be gap for sure. Sorry, let me know. Phi1, phi2, then it must be gapped. But these are mean field gap. But the claim is that if they are disordered, even though the phi1 and phi1 square and their power all are 0, phi2 square, at least for all the terms that occur here are 0, I claim that when they are disordered, which means the phi is fluctuating, and then when you are able to integrate out them, you actually get the same condition derived for the multi-fermion interaction. That should also be gapped. And now let's come into connect to strong CP type of problem, which actually now I'm going to state. Because the problem of strong CP has something to do with so-called the theta term. And yeah. But the theta term is not the complete thing to be physical invariant, but you need to combine with the angular part of determinant of mass matrix. So I'm going to review that. But the main point is that because here I get some kind of a interaction term with some interaction like a mass term, but this mass does not have a mean field mass, but it's so-called disordered mass. Then I can revisit the strong CP problem again to question what exactly is the physical theta if I include the mass or interaction in a more generalized way, including SMG. So that's the thing we are going. Anyone have a question for this? And I can explain a little bit. Otherwise, I'll just show that. Okay, so let me try to go there. So yeah, this is a different writing I was showing earlier for the 345. Okay. 0 model. Yeah. So let me go to a strong CP problem part. So which will go like this. So I will connect strong CP type of problem to symmetric map generation. But because we are earlier was explaining 1+1D model, so actually it's not the same as strong CP that require SU3 non-abelian gauge field. In 1+1D, we have something related, similar, which actually is the theta term for the 1+1D U1 gauge theory. Yeah. Yes. Yes. Say again. Which model?
One with all these cosine size.
Right.
You integrate all this, and then you get
6-body interaction with within 4 fermion. There are 4 sets of fermions, 3, 4, 5, 0, but there are 6-body interaction. It's more than 4-body interaction. Yeah, I can show you that. Upper model, I'm applying to just one side of a boundary. If I have a 2-side, let's say. This one is phi has no map, so I'm trying to compare. I say the mean field map is what people usually do to convince there's a way to gap, but this is not SMG, so this is mean field. So this is not what we want. Actually, we'll consider this symmetry mass, which we need to preserve symmetry. When this phi has a VAP, when the expectation value is non-zero, then this will break the 3, 4, 5, 0 symmetry. But Mignon was knowing we are going the direction to get the gap phase, to get the chiral fermion, but without breaking the chiral symmetry. And that can be done by demanding either this interaction that explicitly preserves the symmetry, but I can also show this way, integrate the phi field, by making the phi has no VAF. But then you need to believe why this works, because this seems no VAF. But what happened is more like, I'm going to draw it. For the phi has a VAF, it's like phi1 is a complex boson with a radius and with a phase. And the VAF means it has a radius and with a phase, and that has a VAF, non-zero. When it says 0, it means actually the phi is disordered. It means the clock is disoriented or randomly oriented, no direction. So the expectation for that is 0. And then it's more like when you come into a place, ask, what time is it? You can ask this one. You can tell me, what time is it? So let's say it's 12 o'clock. But for this one, it's disorder. So this is order phase to disorder phase transition. And this order phase is more like low energy mode, for that would be superfluid mode. I'm going to draw superfluid. And the disorder phase is kind of dual theory. And you change a variable, for example, anything described by vortices of the disorder field. But if it's really random disorder, then this disorder phase is like condensed matter, say, insulator. So it's actually a concept of superfluid to insulator phase transition as disorder theory. So now I try to say the usual way to get mass is order phase, but we are using disorder way. And actually there's a relation to a topological argument from multi-fermion interaction or integrally the many dynamical scalar field induce the multi-fermion interaction. And if you see the clock now enough, then you can know what I'm going to do. I'm going to relate this to the theta term of the strong CP problem. Yeah. Yes. What are the 2 models you are comparing? These are exactly the rewriting of the same model applied on the mirror side. And I apply the mirror side because I want to get chiral fermion left on the other side. And certainly, you can just consider deformation from gapless to gap. But I'm applying the gapless to gap only on the mirror fermion, while the chiral fermion is always gapless. This model is gap on the mirror side, but it's gapless on the mirror side. The gapless side we don't touch. And gapless side is like standard model side. We let everything we happen in the standard model, that the way it is. But we are trying to do something about the mirror side. So it can give you your explanation for parity violation applied to a mirror wall. Right. And Yes. Okay, so now I show this two clock. You can kind of get some sense. I think for condensed matter node, this is so-called disorder insulator, and these are order superfluid. So usual way to get mass is order superfluid, and the way symmetric mass is disorder. And I show different model to connect them. So let's go to the strong CP type problem. Let me just say the problem in a more pictorial, so I don't need to write equation. There is a parameter called theta, which is the the FOHF term. And let me see. Yeah. It comes like this. And this is a term allow, which is basically the Chen class, second Chen class, that you allow for A other than Yang-Mills term. And there's C2 Chen class, and maybe also have a C1 square combination of that. Then the question for strong CP is particle physicists want to know why we are allowed to have a SU3 this term, and which will break T and P. And T is, it will break, let me write it down. It will break T and P. But T is just CP, and P is CT due to CPC theorem. But the reason we emphasize breaking T, not breaking T, CP is because the weak interaction already maximally break P. So breaking P is not something surprising. But CP breaking is more surprising. And there's a CK matrix due to the 3 generations there. Then there's a CP validating angle. So weak interaction there, the CK matrix is weak interaction cause the CP violation. So we are asking the same question for the strong. Then this angle theta, first of all, is not quite physical because due to this anomaly, which I actually just write here, this one, U1, similar to that one, so U1, let me write U1, UG. When you do a chiral rotation on the biofilm on U1 symmetry, you will get a phase to rotate the theta term due to the U1 mixed anomaly with the gauge group, for example, F23, right? So you can rewrite the theta. However, if you have a mass term, as we know in the standard model, then the mass also get a complex phase. I hope this fact is familiar. And that's why the chiral symmetry is broken by the mass as well. But you should remember first, we still use chiral symmetry though to rotate that, even though these two terms are changed. But these are just rewriting of a theory due to the anomalous symmetry transformation. So this still same theory by rewriting. And that means that the real physical theta should be a combination of this original theta in front of trace FHF, the theta term, and the mass complex phase of mass matrix. So it's angular power determinant of mass. So this is called theta bar. So this theta bar will now relate to what I propose to the disorder phase in the SMG. Right. So what happened is that if I write this as a theta, actually there are a few solutions in the past people proposed. One is the Tahou's massless U-quark solution. At that time in the past, people think possibly one of the quark may be massless. If that's the case, then you can rotate the chiral symmetry along the massless quark. And so I kind of try to write this rotation, chiral rotation for different quarks. Then you can rotate theta away to 0, and such and doesn't change any physics. So this is a massless quark solution or Tahou solution. So let me write this Tahou. So anyone know this solution? No, but it's a Tahou solution for the strong CP. Right? So it doesn't consistent with our understanding for the spectrum of the quark. It seems every quark has some mass. Okay, another solution might be thinking about we do have a mass, but perhaps there is some potential of the theta become dynamical such that the theta potential is relaxed to close to 0. And this is a Patrick solution, and which is I will call similar to the superfluid phase. I'm earlier saying it's an older phase, mean field, and superfluid. Yeah. And now for condensed matter, know there's older phase, then can disorder this mass or disorder this phase to a random, and it will be a disorder field. So this will disorder insulator phase. And this will be theta, for example, exponential of that is 0. It has no value. And this theta is close to 0, but EI theta, this one is actually equal to 1. So this one is more like when you come into a a store, you ask what time is it right now? It's like, what time is it now? Tell me. 2:35. So you know exactly the time because the clock is oriented in some way. But this one is like the clock is strongly fluctuating. You cannot even ask what time is it. And that's the way possibly if we don't have measurement theta, either theta 0 or maybe theta is strongly fluctuating. And this is just changing from a superfluid phase to insulated phase. And that means that if we disorder the Petitquin scalar field, we may access that phase. And what I'm trying to summarize is the whole method called here is that if there's any mass 0, then I can actually nullify this definition of theta because I can rotate any complex part of any theta part into the mass phase, and the mass is 0, then it doesn't change anything. It's not physical. And this one is just a superfluid. There's some potential, and this is disorder. Okay, so this is a possibility. But how do you know this makes sense? Again, this is a concept of phase diagram. Condensed matter way of thinking is if some phase exists, and we propose a solution of action Petitquin-like solution of wheelchair Weinberg, and we have spent maybe 50 years, we have not found action. Maybe we are not in the right phase. Maybe the vacuum we propose, we live in is not one we thought we are, but we can possibly live in the other side, or maybe in between the phase transition. The main point of my proposal is that maybe we should look for this type of phases on the other side and thinking about disorder theory. Okay, so any question for now? Yeah, so then this combined with the strong CP kind of problem to the parity violation. So what will happen is, that I'll just illustrate a few model here. Is that in a 1+1D model, actually I should mention one thing before I go here. Is that here I haven't need to combine this disorder phase of a theta angle for the scalar field with the parity violation of the SMG. So I'm saying that this doesn't require gap in the mirror fermion yet, right? So there's a possible disorder phase is not happening in the mirror side. And so then there's still a certain strong CP problem solution apply SMG without the mirror fermion. So these are two different ideas. But I can combine the two ideas together. So such that this disorder phase indeed happen in the mirror side. So there's a choice. And the first choice I was saying is actually you don't need that. You don't need to consider mirror, but possibly just consider the original set of standard model. So this will be changing the picture of the usual case of thinking about mass, like everything is mean field mass as the following. The whole solution is thinking about U car just have a no U car Higgs mass and no mean field mass. Then you can just absorb the theta if a massless U car, right? And suppose we do have a U car has mass. Actually, I don't know whether this will be consistent with phenomenology, but I just go ahead to question that. Suppose a set of a UD and some other set of a lepton, quark and lepton, they form anomaly free within certain gauge group, and maybe they have a secretly some SMG interaction. Then it's possible they can get a little bit SMG mass, but majority of them still get the Yukawa Higgs mass. Then I can rotate the theta away through the SMG, the random disorder mass. So this is the idea here. And this idea does not require a mirror fermion. Okay, so this is still the standard model theory plus SMG interaction. But applied to the mirror fermion looks more like the following: is that just like 3450, we have this chiral and mirror side, and we apply to the mirror fermion. Then the spectrum will contain not just the original chiral theory, but possible the mirror theory, but they are gapped in the mirror way by SMG, which I draw by blue. Then in that case, I can disorder the mirror side of the complex phase of the mass matrix in the mirror side and hide away the theta term. Yeah, so that's how this parity solution can relate. The weak parity violation view from the SMG point of view can combine with the issue of a strong CP. So we can rotate the theta on the mirror side, mirror fermion side. And I did mention the 1+1D model. So like 3450, there's analogous, the theta term, one can write down as a theta 2 pi for the U1 gauge fields, stress F. But in the 3+1D is the theta for the SU3 trace F wedge F. The argument will be similar, but I guess it's more complicated. And also the dynamics is not so clear for sure. But I think the physical principle of this idea, I want to just give you, just demonstrate to you. The idea is similar, yeah, for 1+1 and 3+1. Okay, so I guess I'm pretty much done. Yeah. Any question? Let's see. Maybe I can say something about the energy scale. Is that you'll wonder how much I changed the standard model. I didn't change anything. For example, everything like SU3, SU2, U1, electroweak, Yukawa Higgs, all are preserved. But the only thing that might have a changes above certain scale, SMG occur at higher energy. So in the case of a weak parity violation, we use SMG to gap a mu fermion, and this scale is much higher. And if we go above that scale, then everything seems much more low energy, and then you can think about the whole theory is actually there's a reflection and combined with parity symmetric. So that's why the whole thing has the parity symmetry at some high energy scale. But after SMG is applied, then it can gap the mirror. So we have a weak parity violation here. And that's the idea. And now once the SMG is applied in some set of fermions, if they are all connect to the same gauge field, then you can use either set of complex phase of the fermion to rotate away the theta term in the same set of gauge field that total two set of fermion. Then we can rotate the theta away. Here, this talk, I only try to rotate the theta away, but I didn't ask more about the physical consequence. Maybe there are something observable, something else. So the previous work people compute the theta term is like Veneziano, Wheaton, etc. There are 4 people, they compute the theta term and their effect on the neutron EDM. So these are the calculation involving pions. But I didn't ask further, for example, if I change the scenario, what will be the physical observable, but it could be something new that one need to compute if there's effect like this one. Okay. So this will be the spectrum if I have a mirror side like this. Okay, so let me conclude, I think. I guess I can say a few things because they are general solution. I think I mentioned two methods U quark, and I just make a comment say that U quark is 0, then you can rotate away. And the other solution that pretty cool is make a theta 0 by relax to the low energy of some potential of a theta such that 0 or close to 0 is where it's the lowest energy state. So you can think axion is like a goldstone type of mode. But these are the superfluid-like idea. Well, disorder idea is what we use. But combined with getting rid of Nielsen-Neumia fermion doubling, and that's related to weak parity violation or related to the lattice chiral fermion regularization, and then try to rotate the theta away, but due to the SMG disordered theta. And also combine the idea of the parity reflection symmetry preserved at high energy as a more symmetric high energy theory. Then parity reflection is broken due to SMG gap. So then combine this idea, actually these are the one we talk about today. But actually previously people discussed parity-like solution with Nielsen bar, BCS bar, Chan, Swajanovich. This one has some analogy to what we discussed, but the difference is that they may either need to double the gauge field, or they may need to, they did not consider the symmetric mass generation interaction. So basically everything is like cover Higgs setting. So this is a major difference. But there's some analogy for that solution. In some sense, I think these are, you can think what I talk about is SMG variant or modification of the previous old model in some sense. Okay. Yeah, so I think, yeah, let me conclude. Yeah, so, yeah, I mentioned weak parity violation, and I try to relate to symmetric mass generation. And this actually has something to do with also regularized chiral fermion on the lattice. If I gap a mirror fermion or define a gap boundary on the mirror side, I try to remove the fermion doubling from the Nielsen-Niemeyer theorem by including interaction. In the sense, it's going beyond the band theory. So Nielsen-Niemeyer is more like a free fermion band theory calculations. And so this idea can be viewed as SMG and with domain Wolf fermion, similar to the domain Wolf lattice model like David Kaplan, but not with SMG context in the sense of on the lattice side. But on the field theory side, some people will kind of classify me as doing this on lattice, but I think it's not quite true because I do discuss field theory. So I did discuss SMG in the context of field theory. So, but for the lattice side, I think this lattice domain Wolf fermion is something you can think about. But everything I say is actually can be implemented on the field theory. And now the strong CP problem, I think the new take here we have is we know the question people have is neutron EDM, electric dipole moments, small, so QCD respects CP and T symmetry. But now today we propose possibly they can have some relation to the SMG due to disorder the theta, or in some sense remove the Passivhaus action into the disorder phase. So action is in the order phase, and we go to the disorder phase. Yeah. So that's it. Thank you very much. I should thank many people, Andy, Matt, for the organizing the workshop. Yes, please. Yes. Yes. Right. Yes. Let me see. Sorry, let me just go. I think the inspiration for that one more or less has two versions of story. So if you take the full standard model and if you want to get the set of chiral fermion in the standard model, I think the first one who did this in a way argue from QFT is by this Rosama and David Tone. And basically they used this n equal to 1 smooth confinement cyber duality type of concept to do that. So that one, I think my understanding is that this work for SMG gap in the mirror fermion. So let me see where but I think if I want to apply this concept to strong CP problem, it seems complicated because because one need to define whether there is a complex phase degree of freedom when you write interaction terms. Basically, you want to see the theta terms under chiral rotation. When you rotate it, does it come to somewhere else? And you want to define a physical invariant term. I think the first one, if I, these are separate things. One is SMG gap in the mirror fermion by what this Rosama and Tone did is, I think, it's pretty robust, successful. But now the question is that whether this one can help to apply the strong CP problem I was saying in this case. In the case, I think for Rosama and Tone, that one seems difficult. But actually, I think David, Rosama and Tone, yeah, for the universal. No, let's start with a standard model and then adding additional sector. I do think they probably also supersymmetrize in some way, but I think the outcome of the model can also be just the non-SUSY. I think they use supersymmetry argument to write down the deformations, but at IR, I think you can also just see there's a non-SUSY version of that. But the main point is, I think, for SMG gap in the standard model, I think no problem. But for SMG gap in standard model, but without removing the theta term, I think that's a bit tricky. I have a slide summarize that. Let me just find it first. Let's see, where is it? Yeah, I think here. Yeah, this is what so I think this is difficult for the smooth confinement one. But I think that we also find another one is the mean field deformation. So the idea for that is that it's more like a weak coupling argument with the some scalar field coupled to quark and lepton in a certain way, and there's a mean field deformation such that it can still preserve a deformed standard model chiral symmetry, but can also access the gap phase. But because there the phi is a mean field mass, so if you do the chiral rotation, you can see that phase will become part of things in front the phi field. It's not a disorder phase. So this again work for the SMG gap, but I don't think this is the one that should apply for strong CP problem. So the proposal I will say that is that using this mean field one and writing down the disorder version of this. And what it means is that if I integrate the scalar field and try to introduce dynamical scalar field to generate interaction terms, then I can also write down some multi-thermal interaction terms. Or another way of thinking, just thinking about the scalar's disorder. So in a sense, having phi does not have an explicit mean field mass or the mean field expectation value, but just the expectation is 0. Then in that case, I can apply the chiral rotation on quark again, and it can also rotate the theta, but it doesn't contribute to this one because it does not have a VAF. Yeah, the idea is like this. But certainly, what are the most promising interaction or deformation? I don't know. Maybe one can try. But the main input, I think, the idea I try to bring in is that if the scalar does not have a VAF and there's no mean field mass term, then there's a way you can EO define the theta such that when you do chiral rotation, rotate away the theta angle in the FYGF term, this term still have a zero VAF and it doesn't have a physical consequence. I don't know, does it make sense? Then I can, yeah, I can clarify later if you want to know more. Yeah, so that's a comment. So in some sense, the high dimension model, I think these are the starting point one can use. But personally, I believe if this is really the way it works, then possibly there are other consequences. In a sense, maybe neutral EDN is closer to 0, but there are some other physical perceivable that one can measure. Some higher order effect, I'm thinking. Yeah, maybe quadruple, not dipole moment, but quadruple moment, octuple moment. Yeah. And certainly there's also the concept of disordering. So which is actually go from order phase to disorder phase. And people study duality know that from order to disorder is basically try to go through the phase transition to the dual side. Yeah. Okay. Let me just say one thing. Oh, okay. Any question? No. Oh, sorry, no problem. I'm just saying, just draw this situations that the EM. Let me make it this way. And then weak and strong. So just summarize. What happened in the standard model is weak already break parity, which is a chiral fermion, and weak also break CP, which is T, due to the CP angle of the CK matrix. And today we are trying to relate the weak interaction parity violation here to the strong CP problem here, and to question why that angle theta is breaking P and T, which is breaking CT and CP. And we try to answer why these two things might have a relation by SH. So that's it. This is the standard model. That's it. Thank you.